Hello everyone, my name is AZHARUL Islam and I'm a PhD student at Missouri University of Science and Technology. I work in the area of cryptography, security, privacy and blockchain under the supervision of Dr. Sanjay Madria. So the title of our paper is a Collusion-Resistant Revocable Attribute-Based Encryption Scheme for Secure Data Sharing in Cloud. This is the outline of today's talk. In the introduction and motivation, we discuss first why do we share data in the cloud. After that, we discuss why security is important when we share data in the cloud. After that, we discuss various existing approaches that deals with secure data sharing in cloud. After that, we focus on attribute-based encryption scheme and some of its benefits. Then we discuss the challenges and limitations of existing ABA schemes. After that, we discuss what are the goals that we are trying to achieve, then the preliminaries, our algorithm details, and then our ABE-based secure data sharing architecture. After that, we discuss the evaluation result, and at the end, we discuss the conclusion and the future work. In a typical cloud data sharing scenario, the data owner would upload the data in the cloud and the user will access it from anywhere. And there are many benefits to this, such as it allows easy access and share, it allows high availability, scalability, fault tolerance, and very low maintenance. Though data sharing in cloud sounds very convenient, but its security can be an issue. So the question is, why do we need security? We need security because the data can be very sensitive. Also, the cloud can be malicious, that is, it can collude with a malicious user, and there could be poor security measures and practices in the cloud. And also, the cloud is prone to external and internal attacks. There are various ways to secure data in the cloud. However, the general idea is to use some sort of encryption. For example, the data owner would encrypt the data, upload it in the cloud, and share the decryption keys to the authorized user, such that the authorized user only can decrypt the data, but the cloud doesn't know anything about the data. And there are various encryption schemes that are used for this purpose, such as RSA, identity-based encryption, broadcast encryption, and perhaps the most interesting one is attribute-based encryption. Let's see what attribute-based encryption or ABE is. ABE allows a data owner to encrypt the data with a policy such that the data can be decrypted by a user only if his or her secret key has enough attribute to satisfy the policy. For example, in this case, this policy allows a PhD or MS research student to decrypt the data. So Alice can decrypt the data, however, Charlie cannot because the research attribute is missing in the secret key for Charlie. There are many benefits of AVE, such as it can capture very complex access control requirements, and it also allows fine-grained access control when the data is shared in a group of users. And it is also a very expressive way of encryption because both the attribute and the policy have their meaning. And it also is a one-to-many encryption scheme. That is, the user or the data owner only needs to create only a single copy of the ciphertext. And it is also a user-centric privacy and access control scheme because the data owner selects his own access policy and it allows the data owner with more control. There are many limitations in existing ABE. Perhaps the most notable one is revocation. And we need revocation when someone's key expires or some user voluntarily leaves or we need to remove some user with compromised keys. And this is challenging because in attribute-based encryption, same attribute can be shared among multiple users and removing one user or revoking one user may affect others. And due to revocation, key update may be also required, which adds a lot of overhead. Another important challenge is collusion attack, where multiple users who independently cannot decrypt the ciphertext comes together and combines their key in order to successfully decrypt the ciphertext. And there are two types of collusion attacks in ABE. Let's discuss them with an example. In this setting, this access policy allows an MS or PhD research student to decrypt the ciphertext. So PhD research student Alice can decrypt the ciphertext. However, MS research student Bob cannot because he is revoked. On the other hand, neither Eve or Charlie can decrypt the ciphertext because independently they don't have enough attributes in their secret key. So in type 1 collision attack, Eve and Charlie combines their key to decrypt the ciphertext because jointly they have research and MS attributes, which is enough to satisfy this policy. On the other hand, in type 2 collision attack, Bob, who cannot decrypt the ciphertext because he is a revoked user, colludes with Eve and or Charlie to decrypt the ciphertext. So one thing to notice here is that none of this collision attack involves Alice because Alice can already decrypt the ciphertext. So this combined collision attack doesn't give any additional advantage. So in ideal scenario, we want none of the collision attack to be successful. Unfortunately, none of the existing ABE schemes addresses the challenges that we discussed earlier very well. For example, number 1 and 2 proposed by Hu et al. Are prone to type 2 collision attack. Number 3 is prone to collision attack, and additionally, it requires secret key redistribution by a semi-trusted entity whenever there is a revocation. So, and number 4 and 5 are inefficient revocation because after revocation, the non-revoked user needs to update their secret key, which adds a lot of overhead. Our goal is to address the revocation and collision attacks very well. More specifically, we want efficient revocation such that non-revoked user secret keys are unaffected. And we also want our scheme to be resilient against both type 1 and type 2 collision attack. And we also want secure revocation such that no semi-trusted entity is required in order to achieve revocation. Now let's discuss the building blocks of our proposed ABA schemes. We make use of a hash function h defined as this. We also make use of a bilinear map, which is a function e defined from g times j to gt. And it has a very important property called bilinearity, which suggests that these two evaluations of e have the same value. Access policy is a Boolean formula represented by AND OR gates and a set of attributes. And any subset of attribute that satisfy this Boolean formula is called a satisfying subset. For example, A, B, B, C, D, those are some of the satisfying subset for this Boolean formula. So in attribute-based encryption, what we do is share a piece of secret among the attributes such that any satisfying subset can be used to reconstruct the secret. So in order to do that, first we convert this Boolean formula into a binary tree like this. Then we assign a vector to each of the node by doing a level order traversal. We also use a global counter GC initialized as 1. So first we assign vector 1 to root. Then if it is an AND gate, we create a new vector by adding a 1 to the right of this vector and assign it to the left child. And for the right child, we create a vector with all zeros followed by a -1 that has the equal length of the left child. And after processing an AND gate, we increment the value of GC. But for an OR gate, the children gets the same vector as its parent. So that is the case for this third level because both of these nodes are OR gates. This AND node is processed the same way as the root. After processing it, we increment the value of the global counter. For this AND gate, we can see the value of GC is greater than the length of this vector. So what we do is add a 0 to make it its length equal to the value of GC. So in this case, it will be 1, 1, 0. So with this vector, we treat this AND gate like a regular AND gate and get the vector for its left and right children. So after we are done with assigning vector to each of the node of the tree, what we do, we create a matrix from all the leaf nodes vectors. And we also add necessary zeros to the right to make them equal length. We also use a function called row that maps a row of the matrix to its corresponding attribute. And one thing to notice here is that if we add the rows corresponding to the attributes of the satisfying subset, we will always get 1 followed by all zeros. In the linear secret sharing scheme, M and row is our access policy. So let's assume that V is a column vector where S is the secret to be shared and R2 to Rn are some random values. So in order to create ith valid share of S, what we do is multiply V with the ith row. So if we have the valid share that correspond to all the attributes of a satisfying subset, we can simply add them together, and it will give us the secret S. So that is the case because of this property. So in attribute based encryption, we create the valid share of S during the encryption process, and we reconstruct S with the valid share of the satisfying subset during the decryption process. So how do we revoke user efficiently? Let's assume that we have a binary tree and each user is associated with a particular leaf node, and we want to and RL is the list of users to be revoked. So in this case, U6 and U8. So in order to do it efficiently, we use the subset cover problem that selects the minimum number of nodes that covers all the non-revoked users. So we represent it as cover RL prime, where RL prime is the set of all non-revoked users. And as you can see, we can use just 3 nodes to cover all the unrevoked users in this case. Our proposed ABE scheme is composed of these 4 algorithms where setup and keygen are run by a trusted entity called attribute authority, encrypt is run by the data owner or the sender, and the decrypt is run by the data receiver. In the setup algorithm, attribute authority creates the master key and the public key, and it also creates a binary tree and associates each user to a particular leaf node. And for each node yi, it randomly chooses gy from g. Attribute authority keeps mk as secret while makes the other information publicly available. Data owner run encrypt algorithm to produce this ciphertext CT for message M. So the CY components correspond to the green nodes of this tree. So in this case, if we want to revoke user U6 and U8, then CY2, CY12, and CY14 would be our CY components. And one thing to notice here is that this is the actual message, and it is encrypted by multiplying it with this component. And S is our secret that we use. And this second components, which is CI, correspond to the secret share in the attributes. And as you can see, this lambda I is the secret share, and it is located in the exponent. It is located in the exponent. Attribute authority runs keygen algorithm to create ciphertext SK of user UK for attribute set S. So this KY component correspond to the all the nodes in the path of the user. For example, for user U1, these are the four KY components that correspond to these 4 nodes that is associated with user U1's path. And the second component, KX, correspond to the user's authorized attribute set, which is S. So this is our ciphertext CT, and this is the attribute secret key SK for user UK. In the decryption, what we want to do is retrieve the M, and in order to do that, we'll have to compute this component. To do that, the user takes KY from the secret key and CY from the ciphertext that correspond to the green node in his path, and then computes P and Q respectively. Then the user takes KX from the secret key and CI from the ciphertext that correspond to the satisfying subset of attributes, and with that and previously computed P and Q, the user computes W, which is this one. Note that the secret S is computed in the exponent by adding the secret share by adding the secret share that correspond to the satisfying subset of attributes. And once W is computed, message M can be easily retrieved from C over W. Now let's see how our AB scheme prevents against collusion attack. So for type 1 collusion attack, Charlie and Eve combines their keys to satisfy this policy. Note that neither Charlie nor Eve have enough attribute in their secret key to satisfy the policy. So basically they take MS attribute and research attribute which satisfy this policy and combine them to launch this attack. However, note that the exponent T3 and T2 are different. So as a result, these two components are not compatible with each other. So in order to successfully launch this attack, they will have to figure out either T2 or T3, which is as hard as solving discrete log problem. So this is impossible. In type 2 collusion attack, Bob, who is a revoked user, colludes with another non-revoked user, say Eve. So note that though Bob have enough attributes in his secret key to satisfy the policy, he cannot decrypt the ciphertext because he is a revoked user. Or more specifically, he do not have a KY component that correspond to the one of the green nodes in the tree. However, since Eve is a non-revoked user, Eve has one. In this case, this is KY2. So in this attack, what Bob does is takes KY2 and tries to make it work together with his secret key. And the KY2 correspond to the CY2 in the ciphertext. Unfortunately for Bob, Eve's KY2 will not work with his research and MS attributes because the exponent T2 and T6 are different. And in order to make them work together, Bob must figure out either T2 or T6, which requires solving discrete log problem, so which is impossible, and hence the attack will fail. We propose a secure cloud data sharing architecture based on our AB scheme that we previously discussed. So in this architecture, attribute authority runs the setup algorithm and generates the public and master key. And what attribute authority does is uploads the public parameters to the cloud. Then attribute authority runs the keygen algorithm for each user and provides them with the attribute secret keys through a secret channel. Then the data owner gets the public parameters from the cloud and creates its own revocation list and encrypts the data and upload it in the cloud. Later on, the data users can download the encrypted data from the cloud, and they can decrypt the data with their attribute secret keys if their keys are authorized to do so. One thing to remember is that the data remains encrypted in the public cloud, so the cloud doesn't know anything about the data. For evaluation, we measured the runtime of different algorithms on two different curves called SS512 and MNT224, which are symmetric and asymmetric pairing curve respectively. This graph shows the key generation time for different schemes, and as you can see, our scheme performs better than most of the schemes, and it is pretty close to the baseline scheme. Our encryption time is also very compatible with other schemes, and the decryption time is almost identical to the baseline scheme, which is better than most of the scheme. Perhaps the most significant advantage of our scheme is that our AB scheme do not require key update in order to achieve revocation. Instead, the data owner chooses a revocation list during the encryption, and that enables revocation. As a result, our key update time is 0, which is far better than other schemes. To conclude, we achieve efficient revocation with zero key update cost, and our scheme does not require any additional entity to achieve revocation because the data owner actually chooses a revocation list during the encryption, and that enables revocation. Our scheme is also collision attack safe, and we achieve revocation at the user level. That means a user can be revoked as a whole, but not a particular attribute from him. And in the future, we would love to change that. That means we want to enable fine-grained revocation that will allow particular attribute to be revoked from a user. And currently our attribute authority is not centralized. We would love to make it decentralized in the future, and we would love to support dynamic access policy, and we would love to explore quantum safety in the future. Thank you very much for your attention, and we would love to answer any question from the audience.